bless you. So we looked at these two examples with our Grignard reagent last time to design a synthesis. And the key with this particular question is it's saying we have to start from an alkyl halide and a carbonyl that have 5 carbons or less. So this one gave us a stipulation on what we can start with. So that's just making it to where we have to think about it a little bit more. So our new bond is going to be between our carbon that has our alcohol and one of the other carbons. And of course with the Grignard we need an alkyl halide, which we can then react with our metal. And we need to have a carbon-oxygen double bond. So we already have an oxygen. We know that carbon-oxygen double bond is going to be between our carbon and our oxygen. So looking at this one, this is each one possible route. There are other routes. But in this case, again, we have to keep the amount of carbons with our carbonyl having 5 carbons or less. So that gives us a kind of stipulation of what we can do. So for this one, if we start with this as our C double bond O, then this will be our new bond. So our alkyl halide would be in this position. And of course, all we have to do is take our alkyl halide and add magnesium. Now, one thing to note, this Grignard reagent will not last. So you have to make it right when you're ready to use it. So what I want you to do is when you're showing this, if you start with an alkyl halide, show adding the magnesium to make this Grignard reagent. Because it's so reactive, it does not last at all. So as soon as you make it, you have to use it. You cannot make it and put it in the lab and let it sit for a week. It will not be there anymore. Any water in the atmosphere will react with it. So since it's so reactive, you have to store your starting material as an alkyl halide and make the Grignard reagent right when you're about to use it. So you can't store the Grignard reagent. If we look at this one, our only option for 5 carbons or less is the one in blue. So again, here's our alkyl halide and the magnesium to form our Grignard reagent, which I do want you to show me on a synthesis. So our only route, if we're keeping our carbonyl, if one of them has 5 carbons or less, then we can have this one. Now, of course, this can't be our carbonyl because we can't have a carbon-oxygen double bond between this carbon, so it has to be here. So this is our route. Our other route would be this being our alkyl halide. That's also a route. So I'm only showing one possible route here. The nice thing with the Grignard reagent, it can be tertiary, it can be primary, it can be an sp2 carbon. We can have a lot of different carbons that can be the Grignard. However, it just doesn't last very long, so it's really reactive. So this is just one route for both of these. There's another route that you could take to form these possible structures, depending on what our carbonyl could be this carbon. Then this could be our alkyl halide, and that would be just as true. Why would you do one over the other? Well, it might depend on what you have in the lab. So those are just one way to synthesize these. There is another way, and you should think about them. So looking at this one, we answered this one last time. Our Grignard, our nucleophile is our carbon nucleophile. ETO, that's just our ether, our diethyl ether, and that's just our solvent that's non-nucleophilic and doesn't have a proton source. So we can't do this in water, we can't do this in alcohol. If we have any hydrogen present, it's going to react with our Grignard. So that doesn't work. So here we have a ketone. We're going to get one addition. And of course, when our Grignard reagent attacks, we have to put our electrons from our carbon-oxygen double bond onto our oxygen. The second step, water, or in this case, a little bit of acid protonase. So our answer is A. You should have chosen C, because what's wrong with C? We have 5 bonds to carbon. Carbon can't have 5 bonds. So we can't get 2 additions. We don't have a leaving group. B would be if a hydride attacked. We don't have any hydride reagent. We don't have any source of H negative, so B wouldn't be the answer. And D would be the same thing if a hydride attack, but this is not very isolatable because it has a negative charge. A is our only possible answer. Now remember, if we have excess within ester, like we have here, this is not a great leaving group, but it's an okay leaving group. It's okay enough that when we're comparing a C negative and an O negative is more stable, so that will drive the reaction forward. So what we'll get is 2 additions, which we see with B. So with B, for this one, to see it, it really helps to see your starting compounds. So those are starting. And then our Grignard is the 3 carbons that were added. So as you see, that's your 2 additions of the Grignard. So with our Grignard, when it reacts with the carbon-oxygen double bond, what we're going to form is an alcohol. If we have an ester, we'll get 2 additions, and we will, of course, the product that's not shown here is also that we would have this as our leaving group. Not a great leaving group, but it happens because our Grignard is so reactive. Now, C could be an intermediate compound, and it is an intermediate, but our Grignard is too reactive, so it's going to continue. It's not going to stop at this point. And it's not going to stop here either, because our Grignard is very reactive. So with our Grignard, we're going to get the 2 additions. We will talk about a reagent later on in chapter 21 that will stop with just 1 addition. The Grignard reagent is too reactive to stop. So it's going to do 2 additions that we have next to it. Remember, not a carboxylic acid, because that has an acidic hydrogen. That would just react with our Grignard reagent. And our Grignard reagent would act as a base, which we wouldn't get the new carbon-carbon bond. So like we said, let's say this was our Grignard reagent, and we wanted to get this reaction. This reaction would not occur, at least not the way it's written, because our Grignard reagent cannot work in the presence of an acidic hydrogen. And on our Grignard reagent, we have an alcohol that has an H positive. So we have an acidic hydrogen, not very acidic, but again, this is all about our equilibrium when we're talking about acid base. When we're comparing atom, we have a negative charge on a carbon versus a negative charge on an oxygen. Oxygen is going to be more stable. So our equilibrium lies very strongly this way. In fact, for this reaction, it pretty much only lies this way because this is not strong enough to deprotonate this. So it's irreversible. Our actual equilibrium lies almost 100% this way. As soon as we would have an alcohol present, this thing will deprotonate. And if we look at the pKa's, this one's about 16, and this one is about 50. Of course, that varies if we have sp2 carbon, slightly. That varies a little bit if other things are on it, but in general. So we cannot have an acidic hydrogen. Even though OH isn't that acidic compared to our carbon nucleophile, it's very acidic. So that means that we can't have an OH as a solvent. We can't have an OH in our carbono-containing compound. We can't have an OH in our Grignard reagent. And this example, we're showing it in the Grignard reagent. So if we want this reaction to occur, what we need to do is get rid of that hydrogen. That hydrogen cannot be present, and that hydrogen has to not be there before we make the Grignard reagent. As soon as we make the Grignard reagent, then it's going to come and deprotonate another molecule of itself. And remember, once it does this, we no longer have reactivity at that carbon. So we don't have any reactions this can do, except for if we do a radical bromination, which is a whole different reaction and different conditions, and it probably would be really slow at CH4. So once this happens, we lose reactivity. So we really don't want it to happen. It's really hard. We basically just wasted compound. We can't really do anything with it. So what can we do? Well, what we can do is, before we make the Grignard reagent, what we can do is protect that alcohol. So we call groups that protect certain functional groups protecting groups. There's different ways protecting groups work. We'll talk about two main protecting groups in this class. There's many protecting groups. I took a synthesis class in graduate school, and we did a whole month on just protecting groups. So there's a lot of protecting groups that work with different functional groups that react with them selectively, and then those functional groups can no longer react because they've reacted with something else. We're only going to really talk about two in this whole class. Protecting groups, though, well, first let's look at what it'll do. So let's say we have some sort of group. We take our alkyl halide that has an alcohol, or our carbonyl-containing compound that has an alcohol, wherever that alcohol might be, and we react it with something to protect that alcohol. Then we can do our Grignard reaction. Now, we don't want to make our Grignard reagent or mix our Grignard reagent until that alcohol is protected. So we can't have that present until the alcohol is no longer there. Then, once the reaction has occurred, we want to remove the protecting group. So what do you think we need for a protecting group? One, we need a group that's going to easily and selectively react with our alcohol. And we want it to react pretty much 100% reaction. We don't want any alcohol left. So we want a good yield with this. But the other thing we need our protecting group to do is be removed easily to reform our alcohol. So those are our two things that are our protecting groups. They need to react with our functional group to make it unreactive to whatever reaction we're doing. In this case, we have to make it to where we don't have an acidic hydrogen. So in other cases, we'll be protecting in other ways. But in this case, we are making it to where we don't have an acidic hydrogen. But we need a protecting group that we can easily remove to reform our original material. And it needs to be removed at 100% yield so we can get a high yield of our material, or close to a high yield. It doesn't have to be necessarily 100. So it should be a reaction that's easy to do. Also, it should be a protecting group that is going to be stable in the reaction we're trying to do. In our case, the Grignard reaction. So I'm going to tell you about a good protecting groups for alcohols when you're using an alcohol in a basic media or a basic medium. So that protecting group is a TMS protecting group, the trimethyl ether. So what we have is a silicon that is connected to 3 methyls. And what we form is an old TMS group. What you'll typically see is it written as, instead of drawn out, but you can always draw it out, but you will also see it as OTMS. So that's trimethylsilyl group. Silo is for silica. Don't get this confused with our OTS, our tosylate group that makes our alcohol a good leaving group. This doesn't make our alcohol a good leaving group. This TMS group basically just gets rid of our hydrogen on our oxygen. So therefore it protects it. We no longer have an acidic hydrogen. So it's a great protecting group if your alcohol is susceptible to being deprotonated, because we no longer have that proton. So you can write TMS, but don't get it confused with tosylate. The tosylate group makes it a good leaving group. If this left, we aren't stabilizing the O negative. The tosylate group has that aromatic ring that helps stabilize the oxygen as a leaving group. So don't get those two things confused, because it's wrong. Tosylate isn't really a protecting group. Especially not in these conditions, it makes our alcohol a good leaving group. So oftentimes you see it written as this. The reaction to put your protecting group onto your alcohol is pretty simple, and it's actually very similar to putting your tosylate group on your alcohol. And that's just using TMS chloride, and we can use a little bit of base. This is showing triethylamine. That's the ET is ethyl. There's 3 of them, so triethylamine. You could actually use pyridine as well. For putting the toslate group, we use pyridine to deprotonate it. Here we could use pyridine. Pyridine and triethylamine are both non-nucleophilic bases, so they work really well. Triethylamine is just a little bit stronger than our pyridine, but they both will work for this reaction. So the mechanism is pretty straightforward. It's an SN2-like process, but it's specifically called an SN2-Si because it's not carbon that you're attacking, it's a silica that you're attacking. Now notice, this is a tertiary silica, but we are able to do an SN2 reaction with it. We couldn't do an SN2 reaction with a tertiary carbon. Why can we do an SN2 reaction with a tertiary silica? Well, let's look at silica in the periodic table. If we find silica on the periodic table, it's right under carbon. But what's the big difference between carbon and silica? It has expanded octet and stops. It's very big. It's bigger because it's lower on the periodic table. It has a quantum number of 3, so it's bigger. It has more orbitals. And the fact that the center where the reaction is occurring is bigger is why we can actually do this SN2-like reaction even though it's tertiary. So compare our carbon is smaller, so when the 3 methyls are attached, we don't have any room to attack in an SN2 fashion. But if we look at silica because it's bigger, that means that the methyls are going to be more spread out because silica is bigger. It's going to have a bigger bond because silica has a bigger orbital. So we have more room to attack so we can get that SN2 reaction. It's not sterically hindered. So that's what we're seeing with this particular reaction, is the attack is not sterically hindered. So we get this SN2-like attack. So we just need a good leaving group, and fluorine's a good leaving group. Bromine could be a good leaving group, but usually you see this with fluorine. Usually when you buy it, you buy TMS chloride. So once you put the TMS on there, you can do the reaction. But again, you need a reaction, a protective group that's easy to remove. And TMS is super easy to remove. All you need is a little bit of acid, H3O+, or fluorine. So the fluoride ion will remove TMS. So this is really useful to remove, and then we reform our alcohol. So fluoride, usually the source of fluoride, because F negative isn't very soluble in most things, is this tetrabutylammonium fluoride, or TBAF. So you can put H2O+, or you can put TBAF, and that will remove it. So this is what that looks like. So that's a good source of fluoride ion, because something like sodium fluoride isn't very soluble in most solvents. So that's why this is a better source. There is an issue. TMS protecting groups are not useful if you're doing a reaction under acidic conditions, because the acidic conditions will remove the TMS protecting group. So that's not very useful, and you have to be very careful. It's really easy with just a small amount of acid present to lose your TMS protecting group. But the Grignard reaction, there can't be any acid present, so that's fine. We can do the Grignard reaction easily, because if we had any acid present, that would react with our Grignard anyway. So we have to be very careful there's no acid in our Grignard reaction. So the TMS group, we don't have to worry about it being cleaved because we don't have any acid. But you do have to watch for it in other conditions. TMS is not a good protecting group if you're using any sort of acidic conditions. And in fact, in lab, we learned about TLC, which is done on silica gel. Silica gel is pretty acidic, so your TMS group will fall off in a TLC plate or in a column of silica gel. So you have to be careful. You can lose it really easily if you have any acidic acid present. But it also makes it really easy to remove. So the overall process, you take your alcohol before you make the Grignard. You cannot make the Grignard while the alcohol is present. Or you cannot mix the Grignard while the alcohol is present. And you react with TMS chloride and a little bit of base. The base is there to deprotonate the hydrogen, because of course we don't want that hydrogen there in the final compound. So we get an SN2-like reaction. Then we have our OTMS group. Now our oxygen is protected. You can draw out that silica with 3-methos, or you could put TMS. Again, though, don't put TS. That's a different group. Then you can do your Grignard. So we can make our Grignard reagent, and then we can react it with whatever aceto-1O we want. Once that reaction has been completed, we can remove it with a little bit of TBAF or H3O+. And remember, we're usually protonating our alcohols with a little bit of H2O. So if you put H3O+, you're going to remove that Grignard. So that's typically what's done, is when you stop the reaction of the Grignard, instead of adding water, you just add a little bit of H3O+, and it removes the protected group. But you must show the H3O+ with the protected, because our final product doesn't have it on there. So then we can form two alcohols. So this is true whether our alcohol is on our aceto-1O group or if our alcohol is on our alkyl halide. We just need to protect it because it can't be anywhere near our Grignard reagent. Now if you have an amine, we're not really talking about how to protect those. There are protecting groups for amines, there are protecting groups for sulfurs, but that's kind of beyond this class. So there's multiple protecting groups, but this one you need to know. So again, it's very easy to put on and it's easy to take off. So let's start talking about synthesis. So looking at this one, we have that alcohol and we have a bromine. So we know we can't do the Grignard with the alcohol present. The first thing we're going to have to do before we form our Grignard reagent is protect it. So we're going to protect it with our TMSCO and our triethylamine or pyridine. You can really use both. Once it is protected, then we can do our Grignard. So we know this is carbon 1 because this is our only primary alcohol. So here is our new carbon-carbon bond. So our carbon-oxygen double bond must be in this molecule. Remember, we have to have a carbon-oxygen double bond for our Grignard to react with. We can't mix it with an alcohol because what's our Grignard going to react with? It's not going to attack this position because we don't have a leaving group. It's just going to deprotonate that hydrogen. So we have to start with aceto-1O. So of these two, one of them has too many hydrogens. We're adding, carbons. We're adding 1, 2, 3, 4, 5, 6 carbons. So we see I doesn't have enough carbons. We should have 6. So then we're going to react it with 1 magnesium. We won't get any reaction if we don't react our alkyl halide with magnesium. We need that. Otherwise we won't have the negative charged carbon. And then 2 is going to be this structure, so we have enough carbons. Remember, our total carbons in the end should be this plus this. So we're starting with 3, and then we're ending up with 9. So we should have a total amount of carbons. So once that's reacted, then we can add our, technically H3O plus, and then they put TBAF, which isn't really necessary, because if you're reacting with H3O plus, that should take off all of the protecting group. But TBAF will make sure you take off the rest of the protecting group if they did not come off in the acid. But it comes off really easily, so really that last step B isn't as necessary. But this is how that works. So remember G. If I reacted my Grignard with G, all my Grignard would do would deprotonate that alcohol. So we have to have acetobutano. And we talked about the fact that this won't react with an alkyl halide because it would just do an E2 reaction. It would never do an SN2 reaction. So we have to have a very electrophilic carbon. Partial positive carbon between our acetobutano is pretty electrophilic, so we can get that reaction. I know when it does that. Whatever. Those numbers aren't going to bother us. So we also can prepare phenols. In the lab, phenol is usually produced industrially in the big scale by taking benzene, reacting it with this cumene compound, and then doing a reaction with O2. So that's that, we talked about that auto oxidation that's going through a radical mechanism. And then a little bit of acid will form phenol and acetone. That's not really a useful process in the small scale in the lab. Usually, though, it's not necessary because you can buy phenol pretty cheaply. So to make phenol in the lab is kind of useless. You're really not going to spend time making something that takes this long to do and takes this many steps when you can buy it for pretty cheap. And it's all about when you're in the lab. Sure, sometimes you'll make stuff that's commercially available because it's really expensive, but pretty cheap, so you can really buy phenol. So that's how it's made industrially. Phenol, though, itself is really important. It's a precursor to a lot of pharmaceuticals. We already talked about BHT as a preservative in food, and BHAs. But pharmaceuticals also contain a lot of phenols. So does adhesives and polymers. So they're very much a starting point to a lot of reactions. Here's some antifungal agents that contain phenols. You can see some of these are, they started with phenols, and then now we have ethers. So these are some examples. So phenols are the starting materials for a lot of these. So now we're going to talk about some reactions of our alcohols. And we'll talk about a couple of reactions of phenol, but we'll really leave that to chapter 18 and 19 when we talk about benzene. I'll give you a hint. This is not a new reaction. Why'd you go back? Okay. So we know that if we have an alcohol, we can do substitution reactions. We can do SN1. We have to add some sort of acid to make our alcohol a good leaving group, and then we can get something like a nucleophile to attack. That has problems, though. We know that SN1 will only happen for tertiary and secondary, but secondary, we have issues where we might have carbocation rearrangements. And also remember, we're going to get both stereocenters if we form a stereocenter. So this kit isn't always a very useful reaction. So for SN2, especially if we're talking about primary alcohols and even secondary alcohols, we can do SN2 reactions, but remember our issue was that we had to make our alcohol a good leaving group, which we did with OTS. Now I'm going to show you some reagents that we can use to do an SN2 reaction that doesn't involve adding OTS, which is a whole different step. So the first one I'm going to show you, now these are still SN2 reactions, so they're really no different than what we've done, but I'm going to show you the mechanisms. So one, we can actually use HBr. Typically, making our alcohol good leaving group with hydrogen doesn't work very well because it makes the reaction slow. So that one only really works well for primary alcohols. But the other reagents I'm going to show you is zinc chloride and SOCl2. And we'll talk about why those work without making our OTS a good leaving group. But of course, we can still make our OTS a good leaving group and react it with a strong nucleophile. So these are just some new reagents. So of course, if we react it with HBr, it makes our alcohol in the leaving group, and then we can get our attack in an SN2 fashion. This is a fairly slow reaction because remember, this reaction doesn't work well in the presence of water, just because the protic solvent slows down the process. But if we use zinc Cl2, now first off, we're going to be substituting with chlorine because chlorine's in zinc Cl2. So zinc Cl2 is chlorine and is interacting with metal. So our metal can accept our electrons from our oxygen. And what that's going to do is, in this process, make our oxygen a good leaving group. So we're not adding something else to make it a good leaving group. The zinc is making it a good leaving group. Now this is going to make our oxygen portion negative, but it's going to give it a positive overall charge. The chlorine is coming from the zinc Cl2, so it can attack, and now we have a good leaving group. So this is a nice route if you want to substitute an oxygen with the chlorine, because the zinc is making it a good leaving group. You don't have to worry about reacting with Tosley first and putting in NaCl. So this is a really nice route. But we can also convert it to a Tosyl group as well and react it with whatever. And if we're talking about primary, we're not going to form a stereocenter, and this works best with our primary alcohols. Secondary alcohols, we can make it a good leaving group. Remember, if we're going through SN2, we did the inversion of stereochemistry. That's nothing new, we've talked about that. So this particular reaction is absolutely not new. Another two reagents that can be used for either primary or secondary alcohols is SOCl2 and PBr3. So if we're using SOCl2, what halogen is going to be replacing alcohol? Chlorine. If we're using PBr3, what halogen is going to be replacing the alcohol? Bromine. So if you have a primary or secondary alcohol and you want to replace it with bromine or chlorine, you can use one of these reagents. And these work with secondary. The zinc Cl2 only works with primary, and HBr only works with primary. So SOCl2, usually we need a little bit of pyridine, and I'll show that mechanism. PBr3 works pretty well on its own. And again, if we form a stereocenter, because this is an SN2 reaction, we're just going to get the inversion of stereochemistry, just like every other SN2 reaction. So I'm just introducing you to some better reagents, but it's the same things we've talked about. We don't have to worry about competition of elimination with these reagents, which is really nice. We've had that issue when we're using, let's say, an alcohol nucleophile, an O negative, that we have that competition of elimination. We don't have that with these reagents. So, what happens with SOCl2? Well, sulfur can accept our oxygen, because remember, sulfur is able to have an expanded octet. Let's look at that periodic table again. Our sulfur is under oxygen, it's bigger than oxygen, and it has an expanded octet, so it can have more than, typically what we see is 10 electrons, but we're going to look at sulfur in the next chapter in a lot more detail, and really dissect that functional group. So we're going to be looking at that in chapter 14. So we can get an attack, and typically what will happen is we'll reform a sulfur-oxygen double bond, pushing out one of the chlorines. That will allow a chlorine to be a good nucleophile. So this is a pretty good leaving group. Our oxygen has a positive charge, and it does so because it attacks sulfur. So since it's a good leaving group, typically this is where the pyridine comes in. We want to deprotonate it. And then our chlorine can come in and attack, making this a good leaving group. We actually form a little bit more chlorine. And again, the whole driving force for this is sulfur can have an expanded attack. So we don't have to worry about eliminations, and we don't have to worry about making alcohol a good leaving group, because the SOCl2 does that. So it's not only the source of chlorine negative, but it also makes it a good leaving group. That's why it works so well. It's a very nice reagent if you're doing a substitution of alcohol for a chlorine. PBr3 is very similar. Again, phosphorus on the periodic table is bigger, and it can have an expanded octet, so it's easy to accept electrons. So we don't need a base for this one, because when oxygen attacks, that's going to be an SN2-like reaction. One of the bromines is going to leave. So we're forming our Br negative in solution. Then this leaves really well with the oxygen with the hydrogen attached. So we don't need a base because we don't need a deprotonator. So that makes our stable PBr2OH, which is easy to remove from the reagent, and our product. And again, we don't have an elimination as a byproduct. So know those new reagents, but all of those new reagents we just talked about are just ways to do an SN2 reaction. And of course, we can always stick with the making alcohol with the leaving group with the tosylate and pyridine, which we've talked about before. But these reagents only work if we're substituting halogens to our oxygen. So if we want to substitute this is our nucleophile, we need to make this a good leaving group. So these only work by making the nucleophile in the reagent. So those are very specific. So this is just a reminder. Tertiary alcohols work best with acids because you got to protonate them first to make them good leaving groups. And then for primary or secondary, we can use these. So looking at this one, here we're going alcohol to make OTS, so we can use calcium chloride and pyridine. Then that makes it a good leaving group, but we're replacing it with an alcohol. Why? Well, we changed the stereochemistry. So our nucleophile is OH negative when we're going through an SN2 reaction, because we had the OTS coming forward, we want the oxygen going back. So basically, we did a reaction just to invert the stereochemistry to reform our alcohol with a different stereochemistry. Then we replace it with chlorine. There's multiple reagents we can use to do that through an SN2 reagent. One is that SOCl2 pyridine, but we could have used those other reagents we discussed as well. So know those reagents, but they're pretty easy. SOCl2 has chlorine in it, so clearly you're replacing it with a chlorine. PBr3 has bromine in it, clearly you're replacing it with a bromine. So just look at what's there. Could have also used the zinc Cl2. So looking at this one, this is just an SN2 reaction. So B, just our normal SN2 product. Now let's talk about some eliminations with alcohols. Again, this isn't new. So this is all a review for things we've talked about. So we already know from chapter 8 that if we protonate our alcohol, we can get an E1 elimination, forming our carbocation. We're always going to form our most substituted double bond if we have a regioselectivity. We don't in this case. You do have to worry about rearrangements. So any possibility of rearrangements, that's going to give you a bunch of byproducts. So E1 is not the best route. But for a reagent like this particular starting material, E1 is fine because there's no regioselectivity because any of the hydrogens that we deprotonated would have led to the same product. And there's no rearrangements, it's already tertiary. But for most cases, we won't want to go through an E1. E2 is unlikely because our base is weak. So we need typically acid to make our alcohol good leaving group. So that's what we just call our acid catalyzed dehydration, because we lose water in the process. So our major is always our most substituted, and if we have any rearrangement possibilities, we will get them. So E2 is usually better if we have any problems. So with E2, we need a strong base. So one example, of course, is that we have to make it a good leaving group. We can use our taussig chloride again. Again, don't mix TMS and tauslate. Those are two different compounds. They seem like really close when you write out the acronyms, but if you actually draw out the compounds and compare them, they're very different. So be careful there. So once we make our oxygen a good leaving group, then we can use this strong base, and we've been talking about this a lot with synthesis. A smaller one will form our most substituted double bond. A bigger one will form our least substituted double bond. It's just a review. But with alcohol, we have to make it a good leaving group. These are usually better because we can control what substitution we're getting, so E2 is usually a bit more of a controlled reaction. Plus, since we never form a chlorocation, we don't have to worry about rearrangements. So this is just a review. Nothing I just said in these last couple of slides is new. So next, we're going to talk about, we talked about reductions. Now we're going to talk about oxidizing. Okay, so we have talked about reduction to form our alcohols. Now we're going to talk about the opposite reaction, which is oxidation, which is our forward reaction. So what do we need for oxidation? Well, notice what we're doing. We're increasing the number of bonds to our oxygen. Oh, fire alarm, leave everything in here. I'll lock the door. Make sure no one touches stuff. We have to meet in front of Thomas Aquinas. Well, not in front of Thomas Aquinas, in the little grassy area.
Attention, attention, attention. This is a fire alarm. Exit the building. Attention, attention, attention. This is a fire alarm. Exit the building. Attention, attention, attention. This is a fire alarm. Exit the building. Attention, attention, attention. This is a fire.
Okay, good job. Way to evacuate. Y'all did well. Y'all passed the evacuation process. I give y'all enough bonus points. Okay, so just to finish up the thought I was going through. We are adding more bonds to oxygen, but in this case we're not adding more oxygen. But depending on if we have a primary alcohol or not, we could. So clearly our oxidation agent is going to have a lot of oxygens, just like our other oxidizing agents we've talked about. So whenever we are doing an oxidation like this, typically we're going to have a reagent that has a lot of oxygens. There's also another thing you need to notice. Our alcohol, our carbon has 4 single bonds, but our carbon-oxygen double bond, our carbon has a double bond and 2 single bonds. So what does that mean that we need to have for this reaction to take place? We started with 4 single bonds. Here we have a double bond and 2 single bonds. So we need to what? Get rid of a single bond. So we need to have a hydrogen. Because it's not easy to remove a carbon-carbon bond. That's a hard bond to break. But we need to break a carbon-hydrogen bond that's going to be easy to remove. So for oxidation, we need a hydrogen. A tertiary oxygen. I'm not saying it can't ever oxidize, but not the type of reactions that we're doing. So we're going to look at primary alcohols and secondary alcohols, but tertiary alcohols with our oxidation reactions won't have a reaction because we don't have a hydrogen. So with a secondary alcohol, we only have 1 hydrogen, so we can only get a ketone. Those 2 R groups are still there. With a primary alcohol, we can get an aldehyde. We still have a hydrogen left, so with a stronger oxidizing agent, we can go all the way to carboxylic acid. And notice I did add an extra oxygen. So there's only one type of reaction we can do with secondary, no oxidation we can do with tertiary. But with primary, depending on which reagent we use, we can either stop at the aldehyde or we're going to oxidize all the way to carboxylic acid. So that's the reagents we're going to be looking at. And for primary alcohols, we're going to have some selectivity depending on which reagent we use. So y'all have a great day. I'll see you guys on Friday and most of us in lab.
Yeah, it's not the percent here, like it's here where it's like sum of x minus no, I'll tell you. Come and get my books.
Yes, you can go away by my office.